Hello students, in this video we'll derive the minimal surface equation for a function of two variables. Let's consider the graph z equals f of xy, where x and y lie in some domain D. And we'll just call it D is sufficiently irregular, right? Sufficiently irregular for me to do calculations. When we go deeper into the PDE theory, we'll put some more stringent requirements on domain D. And then we're going to consider the surface area generated by this graph, right? Surface area of this graph is what? Is going to be just the double integral. This would be the area of this function over here, over this region, is going to be the double integral over D, square root 1 plus fx squared plus fy squared dx dy, right? Of course, this is just the component of the normal vector, right? So in other words, if we were to the first fundamental form, this is really just rx cross ry, like that, or it's the same thing as the square root of eg minus f squared. Like, in other words, those are alternative or criterion for the surface area. Now what I'm going to do is I'm going to ask the following question. I'm going to say, among all surfaces, I'm going to find a function that vanishes on the boundary over here. So let's let h map the closure of this set into R, right? 2. I guess in this case, just just R. It's a value function, right? Good. This guy. Be continuously differentiable. And I want that this function h restricted to the boundary of this domain to 0. In other words, this function vanishes as a continuous differentiable function and vanishes from the boundary, right? So it vanishes from the boundary. Okay. All right, and so what we're going to do now is we're going to consider a perturbation of this area over here. In other words, what's going to happen is this function f has prescribed boundary conditions over here. So in other words, there's a boundary curve. And what we're doing now is we're saying, if we look at the plane over here, this is our situation. Here's the y-axis, here's the x-axis, and then here's the z-axis over here. What we're doing is we're considering some domain, right? And then we're going to look at this boundary over here is fixed, right? It's a fixed boundary. And then we look up and we see some function over here, f, right? I can compute its surface area. And then what I'm going to do is I'm going to perturb this thing over here. But what's going to happen is the boundary is not going to change at all, right? So I'm going to consider the function. Let's consider this function. Consider the function f of xy plus epsilon h of xy. I have the same boundary over here because if I plug in the points in the boundary, which is mapped over here, the boundary is going to stay static over here. So in other words, the boundary is mapped to the boundary. Since h vanishes on the boundary, what's going to happen is that they're the same boundary, but you might have a different sort of a different surface over here, but the same boundary, but different surface area, right? Because now the question becomes is, how can I find f, the function f that minimizes this surface area relative to this fixed boundary, right? So that's our question. So question is, how can we minimize the surface area given a fixed boundary? Okay, this is known as the Plateau problem, right? And it's an interesting question, right? This is going to involve a partial differential equation we're going to see. But of course, we're going to use the Euler-Lagrange method, right? So to address this, let's use Euler-Lagrange. So what we're going to do is we're going to say d by d epsilon of the area of f plus epsilon h evaluated when epsilon is equal to 0. So we're going to do an epsilon derivative. So we're going to do, what's this going to look like? It's going to be this expression over here. It's going to be d by d epsilon, double integral over d, the function stays the same, square root of 1 plus f fx plus epsilon hx squared, and then plus fy plus epsilon hy squared dx dy. And we're going to do this derivative with respect to epsilon, right? And we're going to evaluate at epsilon equal 0. Okay, so we're going to do. If we can do this, that will give me a criterion on f under which we're going to have a minimum of the surface area. Okay, excellent. And so now, of course, we can just put, by regularity, I can take this derivative inside the integral, and I do the derivative of this thing with respect to epsilon, right? So if we did that, what we get with the double integral, and so let me evaluate epsilon equal to 0 over d of what? When we do the epsilon derivative, there's going to be a what? There's going to be a, let's see over here. So we're going to have a factor of 2, right? So we're going to have a, well, 2 is going to cancel out because the derivative of the square root is going to give me a 2 in the denominator, right? We're going to have this thing in the denominator, of course. Square root of 1 plus fx plus epsilon hx squared plus fy plus epsilon hy squared. That's in the denominator, dx dy. Good. And then what goes in the numerator? Well, of course, there's going to be a 2 of these things. I've already canceled out the 2, right? So I'm going to have an fx, hx. Then we're going to have a 2 epsilon hx squared plus fy hy plus 2 epsilon hy squared like this. But when we plug in epsilon equals 0, what do we see? We just see this is going to be the double integral over d of fx hx and then plus fy hy over this square root over here. Now, of course, when epsilon is equal to 0, those terms are going to go away. 1 plus fx squared plus fy squared like this, dx dy. And if we integrate by parts, I can put an x derivative over here, right? On this term just with f's over here. So this is going to be negative by integrating by parts and by vanishing the boundary. There's no boundary terms by the assumption that we vanish on the boundary of just what? I'm going to have an x derivative of fx. I'm going to call this denominator over here to make my life a little bit easier. I'm just going to call this whole denominator over here, call that expression, just call that d, fx over d. Of course, d depends on x and y, right? And then plus what? And plus partial y of fy over what? Over d. And these things are all hit with h by integration of parts, then dx dy. And now, since this expression, I would like this expression to equal to what? I want the derivative to be equal to 0. We want this, what we want. I want this expression to be equal to 0 because then I have one more derivative, and that's just a little more of it. It has to look new. The second derivative of this thing is a mess. But you'll see that that's also going to be what? The second derivative is going to be positive, which means you're going to actually have a minimum over here. Okay? Excellent. And so, since this is true for all h, this is going to force the integrand over here to be equal to 0. So this is going to force this equation. It's going to force partial x of fx, now I'll write it out, over the square root of 1 plus fx squared plus fy squared plus partial f, partial y, fy, of course, over the square root 1 plus fx squared plus fy squared is equal to 0 over here, okay? And so, of course, what we really see is this is what? This is going to be just the gradients. So this, of course, is just the divergence over here. The divergence of what? Of the gradients of f over 1 plus the gradient squared, right? Over there. And this equation over here is referred to as the minimal surface equation, right? Of course, you can do the calculation and write this out. You're going to see it's going to be like 1 plus fx squared fyy plus, you can write that form, of course, right? And then when you do the derivative of the denominator, you're getting 2/3 in the factorized. So you can write it as this. You can write this as 1 plus fx squared fyy minus 2 fx fy fxy plus 1 plus fy squared fxx, all divided by this square root over here. I'm going to write to the power 2/3, right? 3/2. So let's write this as a power over here. So it's going to get power 1 plus fx squared plus fy squared to the power 3/2 is And this equation over here is called the minimal surface equation. So this is our minimal surface equation. Okay, great. That's our minimal surface equation. Of course, what we need for a minimal surface, we need this numerator over here. Oftentimes, you're going to see this numerator being equal to 0 as the minimal surface equation because, of course, the denominator is strictly greater than or equal to 0 by the surface area formulation over here. So, of course, what we have over here is we have a quasilinear partial differential equation. So this is a quasilinear PDE. And so what we need to do now is we need to basically try to figure out if we can solve any particular instances of this minimal surface equation, right? And so we're going to see in certain cases, in certain geometries in particular, when you have a geometry where where the first fundamental form is basically isothermal, right? In other words, it's basically strictly conformal. In the conformal case, we're going to be able to make reductions and turn this into a question about harmonic functions or harmonic vector fields, right? But in general, if I don't have such a nice sort of first fundamental form, so to speak, and we'll see this for a more general sort of surface as well, not necessarily just a graph of a function. I can do the same sort of procedure for the first fundamental form and get the same sort of equation in terms of the mean curvature, right? So in other words, what this is going to force is, we've seen in previous videos that this expression over here is of course an expression for h, which of course is just the mean curvature, right? So in other words, if you want to have a minimal surface area, the mean curvature of that function, the graph, has to be equal to 0. So this idea of minimal surface area and 0 mean curvature are basically go hand in hand. They're basically the same idea in some sense, right? So in other words, we need to figure out a couple different things. Number one, is it possible to solve this PDE on a given boundary? That's the first question, right? So that's a strict PDE question. Can you solve this partial differential equation under some certain boundary conditions, right? So I prescribe boundary conditions. Can you solve this PDE, right? Is the solution to the PDE unique? And then what are the qualitative properties of the solution to that PDE, right? So there's lots of intricate questions that relate to PDEs. And of course, we see like the beautiful connections between differential geometry and partial differential equations when we consider this Plateau problem or this minimal surface equation. So it really gives us a sense of the intrinsic beauty of mathematics, that seemingly independent fields sort of come together to answer a question that was only addressed in the early part of the 20th century. Like a very complex problem because the underlying structure of this PDE, the nonlinear structure, makes it very difficult to analyze. So we'll see in further videos examples of surfaces of revolution, ruled surfaces, and then basically parallel translate surfaces that we'll make reductions of the structure of the first fundamental form and see if we can solve this minimal surface equation in very specific cases. Thank you very much.